Transmission of heat. Transmission of heat. Heat transmission takes place in three forms. Heat transmission takes place in three forms. They are conduction, convection and radiation. Conduction, convection and radiation. Heat flow in solids is done by conduction. In solids, the heat flows by conduction, and in gases and liquids, heat flows by convection, and in vacuum, it passes through radiation. The heat passes through vacuum is by radiation. A material medium is necessary for conduction and convection. A material medium is necessary for conduction and convection. No material medium is necessary for transmission of radiation. To understand conduction of heat energy in solids, let us consider a metallic rod, like a steel rod, whose one end is kept in a stove and the other end is held in hand. Then heat flows from stove to the hand. Now let us observe, let us try to understand how this transmission takes place. In the figure, you notice hot end and cold end. At hot end, the vibrational amplitude of the particles, the vibrational amplitude of the molecules will be larger. As a result of the heat given by the stove, the molecules at the hot end, they vibrate with large amplitude. Their amplitude of vibration increases. They collide with their neighbors and thereby they transfer their energy to their neighbors. So the amplitude of vibration increases slowly from left end to right end. The amplitude of vibration increases from left end to right end due to collision. But the molecules at left end will be vibrating with more amplitude, and the molecules at the right end, cold end, they will be vibrating with less amplitude. The conductivity of heat energy, or the ability to transfer heat energy, is measured with a parameter known as thermal conductivity. Thermal conductivity is a measure of the rate of transfer of heat energy, the ability of the materials to transfer heat energy. Silver, copper are very good conductors, so their conductivity values are high. Bismuth and antimony are poor metallic conductors, so their conductivity values are less. Liquids except mercury are poor conductors. All liquids are poor conductors except mercury. To derive a relation for the coefficient of thermal conductivity, the measure of conductivity, let us imagine a metallic rod in the form of a cylinder. A cylindrical metallic rod is placed with its left end kept in contact with a hot source and the right end with a cold source. The left end is in contact with a hot source and the right end is in contact with a cold source, and no heat is allowed to transfer laterally, that is from the sides. Then let us consider the left end is hot end, the right end is cold end. The temperature of left end is theta 2, the temperature of right end is theta 1. The length of this rod is say d, it is cylindrical, its area of cross section is capital A, which will be given by pi r square. Like this, let us imagine a metallic rod. Let us suppose that the rod is in steady state. That means the temperature from left end to right end will be decreasing, but at each point the temperature remains constant. There will be no further rise in temperature at any point of this rod. In such a case, it is known as steady state. In such a state, the heat flow is taken as Q in time t. In time t seconds, the total amount of heat flow through the rod is say Q. then the amount of heat Q is directly proportional to the area of cross section. It is directly proportional to the area of cross section, and it is directly proportional to the difference in temperature theta 2 minus theta 1. The difference in temperature theta 2 minus theta 1, it is directly proportional to the time for which the heat flow takes place, and inversely proportional to the length of the rod, Hence, Q is proportional to A into theta 2 minus theta 1, A into theta 2 minus theta 1 into T divided by D, A into theta 2 minus theta 1 into T whole divided by D. Like this, the value of Q will be proportional. Q is proportional to A into theta 2 minus theta 1 into T whole divided by D. Let us suppose the proportionality constant is K. Then the relation becomes Q is equal to K into A into theta 2 minus theta 1 into T, A into theta 2 minus theta 1 into T divided by D, or K is equal to QD divided by QD divided by A into theta 2 minus theta 1 into T, A into theta 2 minus theta 1 into T. If A is equal to 1 square meter, theta 2 minus theta 1 is equal to 1 degree centigrade, theta 2 minus theta 1 is equal to 1 degree centigrade, T is equal to 1 second, D is equal to 1 meter, then K is equal to Q. So K can be defined as the amount of heat flow for 1 second, through a conductor of length 1 meter, and area of cross section 1 square meter, whose ends are maintained at a temperature difference of 1 degree centigrade. Like this, we can define the thermal conductivity of a material. Using the above relation, K is equal to QD by A into theta 2 minus theta 1 into T, we can define the coefficient of thermal conductivity. Convection. Heat transferred by the actual flow of molecules is called convection. For example, heat flow in fluids. When the temperature of a fluid increases, the density decreases. So molecules move to this region from other regions where the density is high. The molecules try to enter this region from more dense region. Hot air flows out of the room because the density is it is less dense, and cold air comes into the room because it is at high density. Hot air flows out through the ventilators, and cold air comes into the room through doors and windows. Like this, air will be continuously flowing inside and outside. Cold air comes into the room and hot air flows out. This flow is said to be by convection. The method of this flow is called convection. To understand the process of convection, let us take water into a vessel, into a beaker, and let us add pieces of potassium permanganate to the water in the beaker. Keep the beaker on a stand and then heat the water in the beaker. Then the molecules of water at the bottom of this beaker, they receive heat energy and they become hot, so their density decreases. The bottommost molecules, they receive heat energy and this becomes a low dense region. Hence, the upper molecules, the molecules from the top surface, they will be cold and they try to occupy the less dense region. So, they will come down under gravity, they will come down under gravity. Less dense molecules, they move up. Like this, hot molecules will move up and cold molecules will come down. We notice the flow of these molecules if we add potassium permanganate. We notice the motion of these molecules by the flow of, because by adding potassium permanganate, we can notice the flow of movement of these molecules. Other examples are land breeze, sea breeze, etc. Land breeze, sea breeze, etc. Types of convection. Types of convection. Convection is of two types: free or natural convection, free or natural convection, and forced convection. The free convection takes place in fluids. Generally, it is a consequence of gravity. Forced convection. This convection takes place due to the flow of air. Example, cooling the hot liquids by using a fan. By the flow of air, by blowing air over the surface of hot liquids, we try to cool them. This is forced convection. The airflow through the ventilators due to the rush of cool air from below is also considered as forced convection.